Good morning and welcome to Algorithms and Data Structures. Last week, we looked into the O notation and saw that it's an upper boundary when we look at the complexity of an algorithm. The O notation is the most popular notation or most commonly used one. We looked at this plot and saw that f of n is less than or equal to c times g of n. So g of n is the upper boundary, and with this constant factor, or with c, we make constant factors irrelevant. And all of this holds true for all n's given a certain threshold n0. We looked at one term and saw its O complexity, and then we also said we should always say f of n is O of g of n. We should not use this equal sign because it's only there for convenience and it's not an actual equation. We looked at a few terms and we saw when we want to find their O complexity, typically we would just pick the largest order term, remove the lower order terms or ignore them and ignore constants. We looked at an algorithm or at a problem and we implemented implemented various algorithms to solve the problem, analyzed their complexity, and we were able to find an algorithm that is O of n. As there is an upper boundary, there's also a lower boundary for which we use the big omega. In fact, we just flip the less than or equal sign to greater than or equal to sign, and works pretty much the same. We just pick the lowest order term, and we can combine both into the big theta notation, which is an exact boundary where the lower and upper boundary are the same. And we use two constants to make this happen. Then we compared again O and theta gives us a much better analysis actually, but usually it's much more difficult to find. So typically we would work with the O notation and always pick reasonable bounds. There's also a small O notation, which is a proper upper boundary. So there's a less sign and not a less than or equal to sign. And the O tilde as a minor addition, which gets rid of logarithm factors. There was also a quick note on some algorithms may appear to be polynomial, but in fact they're pseudo-polynomial if we use as an input in the algorithm not a list, but for example an integer, and then it could look like that this was actually polynomial, but in fact it's exponential, which is explained in this Stack Overflow article. There's also space complexity. Algorithms not just need running time, but space as well. So space in our main memory, the RAM, and oftentimes we need to make a compromise or a trade-off between the running time complexity and the space complexity. We could cache a lot. Maybe that would lead to eventually faster running times or lower complexities, but we would need more space, and you can do this vice versa. Now we actually have all the tools to look into further data structures because we've seen graphs as a very generic data structure, and we have our tool set available now to analyze the complexity of algorithms. So we can start building data structures and run algorithms on them and try to build them efficiently. We will start with lists as a fundamental data structure, and in the coming weeks, we'll also look at trees, maps, hash tables, and so forth. But we have all the tools available now because we know how to code in Python and we know how to analyze the complexity of algorithms. There was coursework for the complexity analysis. You're most welcome to work on this. After today's lecture, I'm also available here in Zoom briefly in case you have any questions. Otherwise, we'll have a regular lab session and regular lecture next week. Today, we will study lists. And lists are a fundamental data structure. We will see initially arrays as a very simple data structure. We'll see how arrays work and what we can use them for. And then to add flexibility, we will build dynamic arrays, which we also call lists. We will look into the complexity of certain operations, but we will see that with our existing framework of analyzing complexity, we can do this, but we can amend or extend that framework a little bit by using amortization to get better estimates of the algorithms that run on the lists. And then we look at a few variations of lists like stacks and queues, and we looked at linked lists, which are lists that are not based on arrays. In Python, there are so-called various sequence classes, and you have actually worked with sequences already in Python. For example, you have worked with lists, which are natively integrated in Python. Uh, you also have worked with strings, and we've also used tuples. Tuples are like lists, but we cannot amend them anymore. So, and all of them are so-called sequences, and they have something in common because you can index every element with an index k, which runs from 0 up to n, where n is not included. And internally, these sequence classes, they often use arrays to represent that sequence. And what we want to use is an object-oriented approach, concretely encapsulation. So we want to use a high-level interface like lists, tuples, or strings and their methods, but we don't really want to worry about how this is implemented internally. That's the idea of encapsulation. So we hide the internal details. We can make changes to the internal details when we write these classes and change them, but the ones using the classes do not get affected because we offer a high-level public interface. Now, let's study a bit the theory of low-level arrays. Our regular arrays are stored in the main memory, so the RAM, the random access memory. And our RAM is in your computer something between 8 to maybe 32 gigabytes. Um, and I think on my computer it's 16 or 24 gigabytes. Uh, this RAM is organized in bytes. And one byte is, as you know, 8 bits. And each byte has a so-called memory address, which is a unique number. For a very simple RAM or one piece of the RAM, we could imagine it like this. We have this byte, which has address 2150, or this one here, 2158. Each of these addresses refers to one byte. And the reason why the RAM is called random access memory is because I can access all of them with an index in constant time, in O of one time. So I can randomly pick this one here or this one here. The accessing each of the addresses takes O of one, so constant time. And this is something very helpful. It's different to a hard disk or maybe different to a tape, where depending on where you want to access, you need more or less time. But with our RAM, we can assume that it takes constant time, O of one time to access each individual memory cell. And this is something helpful. And so reading out individual entries is very cheap because it's not like you need to go to the first entry and then walk through to entry 2154, but rather you can just use an index. And that's what you have done also when you used, for example, Java or C++ in your first semester when you have actually created arrays. Now, in our Python intro that we did a month ago, we did not actually access the RAM directly, but rather we use lists. And today we will see how these lists use arrays internally and how to build them on our own. A few more notes on these low-level arrays. So far, I've said our RAM is organized in bytes. And if I create now an array, as you have done in Java or C++, you can create an array and you can say you want an array for example, characters, and you want that array to be of, say, 6 elements, something like this. An array, when you create it, always has a fixed size. So you say the array has 6 elements or 10 or 100 of a certain type. And then what happens in a language like Java or C++, you create the array, say for characters. Now we could say, depending on your programming language, a character could be 2 bytes or 4 bytes, something like this, depending on the Unicode that you use. And when you create your array and you say, I want an array of size 6 for characters, and a character is 2 bytes, then you will create an array that is 12 bytes. And when you use index 0, you access the first cell or the first entry, which is 2 bytes. If you use index 2, you access another 2 bytes and so forth. So this is some abstraction offered to you by your programming language like Java or C++. In Python, you can also create arrays, and I'll show you this later, but it's something we will only implement once, and then we will always just use this as a more high-level functionality, and we start building lists, and we will not implement low-level arrays on our own anymore. Now, there are some challenges when it comes to these arrays. We've just said yes, we can create some abstraction. We say we want an array for 6 characters, and then we get these 12 bytes, but we don't need to bother about the individual bytes anymore, because to us as a programmer, it just looks like this, that I access the indexes and I can read or write in constant time in the individual elements. But there are some constraints. Each cell in a low-level array needs to be the same number of bytes. So I cannot just say I want, I don't know, I want 6 entries, and 2 entries should be 2 bytes, 1 entry should be 4 bytes, one should be 1 byte. It doesn't work this way. So all the entries have the same number of bytes. So what would happen now if, and I said it's a fixed size, so I need to say from the beginning, I want 6 elements or 10 elements. What happens if I run out of space? Say I wanted an array for 10 elements. I want now to add an 11th element. Does not work. I would need to create a new array and copy everything, but I cannot extend the size of an array because the array has a fixed size that I set in the RAM. And maybe if we look at this, the array ends here, and after it, maybe some other variable is stored in the RAM. So I cannot just extend that array. And I also could think, well, early on, I created for maybe a very large size. So I could say, I'm able to store enough entries. I could create a huge array with 1,000 entries early on. I can do that, but that would be a lot of waste because I need to reserve that space upfront. And then maybe I don't need all of that space. Maybe I just need a tiny piece of that space. So I would just waste a lot of space, which is also not very good. I've also said each of my entries has the same size. But what if I want an array now, and that array should store strings? So each entry would be a string, but the strings are varying size. So I would sort of need to define a maximum length of a string, and that would be, say, 50 characters, and then each entry in my array would be 50 characters. But also that isn't too great because maybe a lot of strings are much shorter than 50 characters. Some strings are maybe longer, and then I also wouldn't be able to clue them in. So what we would then build is a referential array. So in our array, we are creating, for example, 6 entries, because I say I want to store 6 strings. We are limited by the number of strings that we can store because we cannot grow the array, but in the entries of the array, we are not storing the actual strings, but we are storing them somewhere else in the RAM. And all we are storing in each entry of our array is a reference to, or a memory reference to where that string is stored. So this already creates a little bit of flexibility because I'm storing these strings somewhere. I can maybe still change the strings, I can change individual elements, but the strings are still stored somewhere in the RAM. Again, these strings would each be stored as an array somewhere in the RAM. So I cannot grow or shrink the individual entries, but the entries can have a varying length because each of them are stored somewhere else in the RAM. And in my actual array where I wanted to store the strings, I'm storing addresses to the other arrays. So each of them is another array. So this already adds a little bit of flexibility, yet unlimited, because if I want to add more strings, my array is not large enough. That's a challenge, but we've added a little bit of flexibility. But now we want to improve this. And for this, we will need so-called dynamic arrays. And dynamic arrays are also lists, or also called lists, because they address the following need. In reality, we often do not know the exact number of elements. Could be 5 entries, could be 1,000. We don't know. We don't want to reserve a lot of memory in advance. So we need a dynamic approach that allows us to grow or even shrink over time. Because maybe we delete a lot of entries and we also want to shrink that array. And these dynamic arrays are typically called lists, and we will work with the term lists from now. And our lists will offer a very interesting feature under the hood. We want to have a list that is a class, we will implement it soon, and internally it uses an array. And that array has a fixed size in memory. But we are unable to grow that array. So what we need to do if we run out of space in that array is we need to create a new array with a larger capacity, then copy all the entries from the old array into the new one, and then use the new array from then on and get rid of the old array. And this is also visualized here. So imagine this is so we have a high level class for a list, and internally we use the array, but it's encapsulated. So when you work with the list, you don't see the actual array. You're just using a high level class that offers certain methods to you. But now we've run out of space. We have 4 entries and they are full, but we are not storing the actual entries in the array. So these are the actual objects. Could be strings, could be characters, whatever. So these are just objects. And this is our array A, and each entry refers to the memory where the actual object is stored. But now A is full, and I want to grow A, which I cannot, so I can create B. And in B, I would copy the memory addresses. So the entry that was in A0, this is index 0, I would copy to B0. And I do this up to A at position at index 3, and I put it in position 3 of B. So I just copy the memory addresses to these objects. I'm not copying the actual objects because they are anyway somewhere else in the memory. And then I say, well, B is the name B referred so far to the new array, but I don't need the old array anymore, so I get rid of it. And the variable name A that I use internally in my list now refers to the new array. Does this make sense to you, this approach? Copying the entries and then getting rid of the old array. Maybe just confirm with a thumbs up or something if that concept makes sense. So, looks good. There is something we did, it's called a shallow copy. A shallow copy means I'm copying the array, but I'm not copying the actual entries. I'm just copying the entries that were in the array or these memory addresses that were in the array, but I'm not copying the actual objects because right now I don't need to copy them because I'm just switching the array. But say if you want to copy, if you need a copy of A, so you want to keep A, let's assume we're not working on a list, but we want to copy, or we're not working on resizing the list. Say you want to copy the whole list, because you need a duplicate of the list for further processing. If you do this the way we have just done, that would be a shallow copy. A shallow copy means we're just copying the memory addresses, but not the actual objects. And then if you use B to manipulate the actual objects, A would also refer to the objects that were actually manipulated. That's a shallow copy. If you want to copy the whole array, including the objects to which we are referring, so you would also want to copy these ones, that would be a deep copy. The difference between a shallow copy and a deep copy is explained in the Goodrich book in chapter 521. You should have a look and read this. You don't need this right now for growing the array, because we don't need to copy the actual objects. We just copy the memory addresses. But if you ever want to copy the whole list later on, you want to have a second list with all the same entries, and you don't want to change or you don't want to manipulate the entries that are shared, so that both A and B would refer to these manipulated objects. If you want to copy the objects as a whole, you need a deep copy, and the book covers this and shows you how to do this. It's not relevant for today for the intro to lists, but it's something you should read in the next few weeks just to revise and expand your knowledge on shallow and deep copies. So we have now done the theory of how to grow an array. So I would suggest let's actually implement this. And as usual, I will offer a live coding session and show you how you can actually build the concept we have just done. We need later a package that is called C-types, and C-types will help us to actually create the low-level array. But that will come at the end. So I want a new class that I call myArray. And we want it to work quite similar to this native list class in Python. So we call it myArray. You could also call it myList, whatever. But it's a dynamic array, so a list. And it will actually work quite similar to the features offered by the native list in Python. And we'll see how this can be implemented. I need a constructor or initializer with no parameters initially. And we need to know the length of our list. And we will use the notation here. So we create an attribute and we use this underscore n just to indicate that n should be considered private. I told you in the intro to Python, there's not really the concept of private in Python. Everything is public, which is quite different to Java or C++. But because of encapsulation, we want to note which elements or attributes or methods should be considered private. They are not private, but just for consideration, we use this underscore. So this is the length of our list, 0. We want to have a certain capacity. So how many elements can our array store? We could say 10, but I want to show you that growing very soon. So we will say it has capacity 1. So initially the array can store 1 entry. And n and capacity are two different variables or attributes, because the capacity says how much we can store at the most, and n contains how many we're storing right now. And initially we're not storing any element. And we will also have an attribute capital A, which will be the actual array to which we are referring to. And for this, we need a helper. And this is called make array. We also want to consider it private. So we put an underscore there. We need to implement it later. And what I want is that this make array creates an array of a certain capacity. So we'll have a parameter for a capacity, and we could put in 10 or 100. Later, we will pass varying values to make array to create ever larger arrays. But initially, we want to create it for the capacity that we specify. So initially, we will just create an array for one element. You could wonder, why are we not starting with 10? We are starting with one, and then later we will grow it. And I'll show you the theory of how we should grow it, so it actually comes with a low complexity. What we need to do is now we need a few helpers. And what you remember is when we worked with lists in Python, I could call something like len of a data structure. And this always returns the length, so how many elements are in the data structure. But somewhere, when you create an object L of the list and you call the len function, which comes natively with Python on L, somehow we need to return the size of the data structure. And if you call the len function on a data structure, it will always look for a method that is called len and starts and ends with two underscores. This is a convention in Python. So whatever data structure you call the len function on, it will look for a method len ending and beginning in two underscores. And all it needs to return is our length, which will be initially 0, later 1, 2, when we add more elements, and we reduce it when we delete elements. What I also want is an index. Remember, if I have a list L and I want to call an index, say index 4, for reading, I somehow need to pass this index as a parameter to my list and read out the value that is there. And in Python, there is a getItem method, which needs to begin and end with two underscores, which is called by Python then if you use indexing. And the k is passed as a parameter. And what I'm returning is self.a at index k, because I can index our low-level array that is yet to be created, because we will do this in make array later, and I can pass index k. Does this always work, or could something go wrong here? If you think this all looks fine, positive reaction. If you see a challenge, send me a negative reaction. So we got a negative reaction. Do you want to tell us what could go wrong? Either turn on your audio or send us in the chat what you think could be going wrong. We got the right answer. K may be out of range. Yes. K could be too small or too big, and it could access an index that does not exist. These referential arrays, so these low-level arrays, they only accept indexes 0 up to n minus 1. I cannot use negative indexes, and if I use an index that is too large, it will also fail. So what I should say is I need to check if k is in the right range. And in Python, I can do this very neatly, and I can say, if k is not in this interval, then do something. So because k needs to be 0 or greater than 0, but it needs to be less than n. And what should I do now if I found an invalid index? For the one who wrote that k could be out of range, what should I be doing now, or what could I be doing now here? I'll see if you have a suggestion what I could do here. There's lots of opportunities I have here. I could maybe just not return anything, but that wouldn't be good because we expect some proper behavior. And we got the right answer here in the chat. The suggestion by a different student is we should raise an exception. And that's exactly what we should do. Exceptions are sort of errors that I raise, and they will terminate the whole program unless they are being caught and handled. And this is the right behavior because we're doing something that isn't possible. So we should not just stop. So the wrong thing we should do is maybe The wrong thing would be not to do anything, just not return anything or just return -1 or print error. That's what we should not do. We should raise an exception. And in Python, you say raise, and there is a class, it's called index error, that's already available in Python for us. And we can pass a text and we can say invalid index. So if the index is not valid, raise an exception. Otherwise, if it's valid, return the proper element. We also need to be able to append. So append means adding an object at the right end. And what I can do is, well, I can say I'm adding one element. So I'm increasing n, and I can look at A at index n and put the object there. Remember, initially n is 0, so I would put the object at index 0, but this n should only be increased later. So something like this. Initially, n is 0, and I'm putting the object there, and then I increase n. And then n is 1, the next object would be put at 1. What else could go wrong here? Anyone sees, if you think this all works fine, green reaction. If you don't think it goes well, maybe red reaction. Or tell me in the chat what could be happening when I try to append. Well, what can happen is that my array is too small, because initially I create the array with size 1 or capacity 1, and then I add one element. That's fine. But if I want to add a second element, my array is too small. Maybe just send some reaction if this makes sense to you, that I may just run out of space. So let's address this. We could check before if n has reached the same value as our capacity. So if I've added one element, n is 1 and the capacity is 1. And then that means I cannot add more elements to the existing array. So what I need to do here is I need to resize the array. That's just the process we have seen before, where I create a new array. I copy all the existing memory addresses and I get rid of the old array. So I can say I will resize, and resize is another helper to be implemented. And what is very common is that I double the capacity. You may be wondering, why don't I do factor 1.5 or factor 3? 2 is a very common choice, and we will look at the theory very soon and see why factor 2 is overall quite helpful, also from a perspective of complexity. So now we are almost done. All we need are two helpers. We need to implement resize and make array. We can start with make array, because we are using up here make array. It's still to be implemented. And what this does is I want to create an array and return it, and I want it to have capacity C. And for this, we need the C types package. And we got the right comment. Yes, this is an underscore A. And I forgot the underscore. Thank you very much. In the slides, it's obviously correct. Sometimes there are typos, and we'll later see if it actually runs or not when we test it. So if you spot any other typos, let me know. Otherwise, we'll see it when we run it. And there's one question by a student why we don't just add a 1 on the capacity and say, We actually want to do like capacity plus one. We could do this, but I've said later in a few minutes, I will tell you why doubling is actually interesting also from the perspective of complexity. Just trust me for now that doubling makes sense. We'll later compare this to your suggestion by adding one on top. And this is one line I personally also don't know by heart, and it's something you will not need again in this course. You only need this once. This C-types package in Python allows us to create low-level arrays. And the ctypes.py object gives us such a low-level entry, and I want to know, and I want to have this C many times because of C means the capacity, and then I have some object that I can call. From my perspective, you don't need to remember this line. I will not quiz you on this in the exam. It's just some low-level call in Python to create our array, and it's being returned. So here we called it and we stored this in A. And we also need make array now when we resize. So resize is the last one to be implemented. And what I want to do is with resize is the figure we had looked at before because our array is too small, so we need to grow it. So what we wanted to do is create a new array, copy the memory addresses from the old one to the new one, and then get rid of the old one. So we said B is the name for our new array. So we make an array for capacity C because C is passed and we suggested it could be double or plus one, whatever, but we are passing a new capacity and we want to make an array of that capacity. Now, what I need to do is now I need to copy all the old entries or the memory addresses in the old array to the new one. And this will work the following way. I'm going through an index k from 0 up to n minus 1, because the range, the self.n, is an upper boundary. And I can access the old entries like this in A, and I can store this in bk. So I'm from 0 up to n minus 1, I'm accessing the corresponding element in A, which is a memory address, and I store this in B at the same index. Now I said I want to get rid of the old A, but A internally always refers to our current array. So I can say self._A will refer to B from now on. So to the array that B was linked to so far, the new one. And I need to update my capacity with the new capacity. So this is my suggestion how we can implement our list. It's a very simple list. What we can do is we can create it, we can read its length, we can read elements, we can append elements, and we can resize. We could do more like changing elements, deleting elements, but all of this will come later. One question to you. I'm just saying self.a refers to the array that B is referring to. What do I need to do about my old array? Do I need to delete it manually or not? If you think maybe we still need to delete something, send a green reaction. If you think we are all okay, send me a red reaction. One person thinks we still need to do something. If we are in a language like C++, we would still need to do something. We would still need to delete the old array that A was referring to. But we use Python, and in Python, we have the same advantage like, for example, in Java, where we have a garbage collection. Have you ever heard about garbage collection? Maybe just send some reaction if this is something you have heard about before. With garbage collection, unused entries in the memory will be cleaned from time to time if no variables refer to them anymore. And A refers now to the new array. So we're not referring anywhere to the old array anymore. So this will be deleted by the garbage collection. So we don't need to delete it manually. So we have created our own array. And let's actually look at it and let's test it. So we can say A is my array. I'm creating an instance, and we can read out the length, for example, which is 0. If I try to access an index 0 where nothing is stored yet, I get an exception as I wanted because I'm not allowed to read out something that does not exist. We can also look at the capacity, for example, and we see the capacity is 1. It's private, but meant to be private. We can still actually access it. And now let's append something. We can append a 42. So if we read out the length of A now, it has changed to 1, and index 0 is 42. If I add now one more element, say a 99, I have a 99, and now the length of A is 2, because A0 is 42, A1 is 99, and A has a capacity of 2, because the capacity is always doubled. If I now append, say, a 1000, I see the length is 3, and the capacity is 4. And if I add, say I append another 1000 and then a 5000, we will see we have 5 entries and we have a capacity of 8. So we can keep adding more elements. So we see it's actually not that difficult to build our own initial list. And this behaves more or less the same as if you create a list in Python like this. The type of our L is a list, and the type of our A is an object of our my array that we have just implemented. Obviously, the native list in Python can offer much more features because we can use an index also to amend elements, but this is our beginning of how to build such an array on our own. Now, this is something that works, and you find the code also here in our slides. And very importantly, if you implement this on your own or you need an implementation, don't copy paste from the slides. This typically leads to chaos. Rather use this resources file I have provided in Nextcloud to you, where you find all the relevant examples. And if you take a look into your coursework, there's also the my array implementation we have just done, and you are tasked with extending it by implementing some more methods. Like we have a get item, there's also a set item, and set item has one more parameter, and with set item we can index k and we can assign a new entry. So you would say a at entry k is equal a value. So you should implement this and wonder, do you need any exceptions or not? You could also think about removing an element and maybe inserting an element at a specific index. But the index also needs to be valid. So you can think about how such methods could be implemented. And if you need examples, just test this with the native Python list or look at its documentation. It will provide you with some advice, and you can try to implement this on your own. And you can also have problem 9.3 and extend the get item to also allow negative indexes. Remember, in the native Python list, we can use negative indices, where -1 would be the rightmost element, -2 the one to the left of the rightmost element, and so forth. So you could also think about how to implement get item, that it also allows valid negative indexes. So you would need to amend your get item a little bit. And there is also some initial exercises about lists in the Goodrich book. So you should do this coursework to understand what we have done a little bit better and get some more practice in improving your own list implementation. What I said is this line here, you probably don't need to remember this one. I personally also just looked it up again, because you will hardly in Python implement something like this again, where you create a low-level array. Rather, you just use this method as a helper. And how to implement this one line, you can probably forget. I will not quiz you on that return here. So we are using these low-level arrays, and we have built encapsulation around it with our length get item append. And internally, it somehow resizes, but this is not something available to the programmer using the class, because resize is, again, meant to be private. We can think a little bit about the complexity of non-mutating behavior. Non-mutating just means, for example, reading or copying, but not changing it. And if I read out the length, this is constant time, because if I read out the length, all I have done was return self.n. And that's obviously constant. When we access the index and said, I want index j, that's also constant, because I'm just using an index on the low-level array, and that is also constant. And when you use the Python list class, it comes with far more methods. For example, it allows you to count a certain element value, and count. So you want to know how often does a specific value appear in your list, and you could just go through from the beginning to the end and check each entry if that's the entry you're looking for, and then count. So obviously that would be O of n, because you need to visit all your entries. Feel also free to implement the count method for your class on your own. And for your native list class in Python, there is more. You can check if a value is in it. You can compare two lists. You can do a slice index. You can concatenate two lists. So these are some further methods that we have not implemented, but feel free to implement them or think about it. And here is a suggestion of what the running time looks like for the native implementations in Python for the list and tuple classes. The space complexity is always O of n, because n is the current number of elements in the list. So the space complexity is O of n. In fact, n is the current number of elements, but the capacity may be a little bit more than n. But the capacity is the memory footprint we're using, because the capacity that is used as the size for the underlying array, but it's just a constant factor of more elements that we have reserved, because we said we always double the capacity. And one of the students asked, why do we double and don't just add one on top? And this is something I also want to discuss with you now. And we will look at the complexity also of appending, so mutating our list. So we will look at this now. And remember, I'll go back to the implementation and then show you what our challenge actually is. So this is what we have implemented. And somehow we need to resize the array. So we have initially created it, and when we append it, we may need to resize it. But resizing is very expensive because in resizing, we need to create a new array and we need to go through all of the elements and copy them. So that's O of n, but in fact, it's an omega of n because I need at least n much time to perform because each of the entries needs to be copied. Now, one of you wondered why I double the capacity and I could just add one on top of the capacity. I could do that, but then I can just add one more element. And if I want to add another element, I need to resize again. And that means I need to go create a new array and copy all the elements again. So resizing is expensive, and I don't want to resize all the time. So rather, when I resize, I create a spot for more elements, and the typical strategy is I double the capacity, and then I have enough elements left for the foreseeable future, typically. And if I need all of that space, then I need to resize again. But the resizing happens less and less often because I always double the capacity. So that's the rationale for copying and or for resizing and not just adding one on top of the capacity, but rather creating more space. So I have 8 elements at some point, then I have a capacity for 16 elements, then 32, and so forth. Now, resizing takes O of n much time. And because resizing takes O of n much time, I want to know from you, from the worst case perspective, what would be the complexity of append? Because we always assume the worst case complexity. Maybe tell me in the chat what you think the complexity of appending would be. O of what? Like to see some guesses of you in the chat. Well, then I'll explain it. So these operations here are constant time because all I'm doing is I'm accessing an index, I'm assigning an object, I'm increasing n. And this one here is constant too. I'm just doing a comparison. But it may happen that I have to resize. And with our O of n, we always assume the worst case complexity. And in the worst case, yes, I need to resize, which takes O of n much time. So in the worst case, appending is O of n. But the resizing does not happen all the time because if I double, it only happens from time to time. But still, we say the worst case is n or O of n because I need to copy in the worst case. Even though the worst case becomes less and less likely. And this can also be visualized like this. Say, I add one element, I'm fine. Because I have an empty list or an empty array of capacity 1. I'm adding one element. But in order to add the second element, I cannot just add the second element, but I need to resize to size 2 or capacity 2, and I need to copy the old element, and then I add the new element. And what you see with this plot is you only need from time to time spend a lot of time on the operations to copy everything. But say if you have reached size, if you have a sufficiently large array and you have enough capacity and you add more elements, then you have that capacity. And only when that capacity is full, you need to resize again. And this plot here shows very well why I actually double and don't just add one on top, because by doubling, I create always a larger free capacity and I can add more elements. Obviously, this will get large and say if you have 1024 elements and you need one more, then you have 2040. So 1024 elements and you double, you have 2048. So you have a lot free. And what may happen is later on, you may actually not append elements, but you may remove elements and say maybe you remove and you only have 100 elements left, but you have 2048 capacity. So when you implement remove, you would also implement that at some point this would resize. If your size is under some threshold, say maybe the number of elements you have is less than a fourth of your capacity. And then you would also resize and create a new array that is actually smaller. So this is something you could think about also in the coursework when you implement remove for resizing. Maybe the current number of elements you have is less than a fourth, for example, of your capacity, and then you would resize and build a smaller array. So it's something you could try out when you implement remove. So this is the rationale why we want to double the capacity and not just add one on top. But with our implementation, our appending is O of n, because that worst case may happen, and we only care about the worst case so far in our O of n. But it turns out that worst case is not happening that often. And what we can do is we can use a framework that is called, or an approach that is called amortization. And with amortization, we apply our O complexity framework to mutating behavior that is, for example, used in lists, but also for trees and for other data structures. And it comes with the following considerations. Imagine you have an arbitrary array of n plus 1 entries. So you have n plus 1 entries. Or let's start with an array of size n, and you want to add element n plus 1. So what we need is, we need to resize n because we have size n, it's full, and we want to add element n plus 1. So we need to resize. And resizing is not just O of n, but it's theta of n, because it takes exactly n much time to resize. But for the next many elements we are adding, we can now add a lot of elements until we need to resize again. And if we don't need to resize, if we have a capacity that is large enough and we just keep adding elements and we have enough capacity, then just adding that takes constant much time. And this can be reflected with our complexity framework. We said we once need to do our resizing, which takes theta of n, but once we have resized, we can add n many times an object. So resizing is theta of n, but adding an object without resizing is O of n, or here also theta of n, and we can do that n many times. So and if we have n plus 1 elements that we are adding to a list or to our dynamic array, from these n plus 1 many times we're adding something, we only need to resize once, and n many times we can just add an element without resizing. And if you take the average from that, then you will see that actually in average, this takes theta of 1 much time. Because from n many elements I'm adding, once I need to resize, and n many times I don't need to resize, I can just add into the free space I have available. And in average, this takes theta of 1 constant time. So we've said that, and if you're wondering about this amortization approach with a few more examples, this is also shown in the book, but it's quite a contrast to what we have said before, because before we have always said we would just take the worst case with O. But actually, this worst case is rare. So that's why we're introducing amortized complexities, and they look something like this. So we're appending a value. We said the worst case is O of n. So theoretically, if I want to know the running time complexity of append, I need to write O of n. But with these dynamic data structures, we saw that this only happens very, very rarely. And in average, it takes O of 1 much time. But I cannot just write O of 1 because we always assume the worst case. And if you want to write out these amortized complexities, you would write O of 1 and a star behind. The star is in the literature the convention for amortized complexities. And we don't need amortization for all of these operations, like for the non-mutating one, we just use the regular O's. But for the mutating ones, it can happen that we, for example, need to resize. But O of n is a clear statement, but it happens rarely. And O of 1 amortized gives us a much better understanding because it's only very, very rare that we actually need to resize. If you are asked about complexities, say in the exam or somewhere else in a report or in a documentation when you work in a job and you need to write complexities, don't just write O of 1 when you mean amortized. Either put a star or behind write amortized or explain that the star means amortization. Because if you just write O of 1, it's wrong because it's not O of 1, it's O of n, but it's O of 1 amortized. So, and you need amortization, or amortization is helpful to describe not just appending, but also inserting, removing elements, and so forth. So, amortization is a very helpful concept. And it will help you to express maybe more realistic O complexities, because if you put O of n here, it's technically correct, yet it happens rarely. So you would write O of 1 amortized. Maybe just confirm with a positive or negative reaction if you got the difference between the regular complexities and the amortized ones. So only see positive reactions. Good. And the concept is again explained in the book if you wish to read more about it. So the good thing is we have now implemented our first list, and we will implement a few more types of lists today, and we'll just introduce slight variations of the list. And one thing that is helpful, not only for lists, but for the remainder of this course, is that we work with so-called abstract data types. And abstract data types are a mathematical model of a data structure. So it's a high-level specification of a data structure. And with an abstract data type, we would describe which type of data is stored in this data structure, which operations we offer to work on our data structure, but we only look at the public interface because we use encapsulation to shield the inner operations that we don't need to see from outside. And for each operation, we would also define the types of parameters of the operation. So with an abstract data type, we define or specify each operation, what we would specify what each operation does, but not how it's implemented. So it's more like a high-level description of the interface and what we are storing. And these abstract data types are something we will see throughout this course. When we introduce a new data structure, we will first introduce the abstract data type and describe high level what each operation would do, and then how to do it. That's what we would implement next. And we will now introduce a new data structure. It's almost like a list, but just a variation of a list. It's called a stack. Who of you has ever worked with a stack? Maybe send some reaction in the chat or whatever. If you've ever used a stack, green reaction means yes, you have used a stack. Red one, you have never used it. So all of you use stacks every day. In fact, when you use an operating system and you call new functions in the operating system, each time it uses a stack internally to handle this. But we'll see applications of the stack later. First, we'll start specifying what a stack is, and we will implement it on our own. So with a stack, we have a stack S, and it only allows two methods initially. We can push something on the stack. So we have an element E and we put it on top of the stack. If the stack is empty, element E is just a bottom element of the stack. If we put another element on the stack, we just put it on top. So we always put elements on top. So we stack them up. And the other operation is popping. And popping means removing the topmost element and taking it. And then if you pop again, you take the element that is currently at the top, and so forth. And you can keep popping until your stack is empty. And if you try to pop from an empty stack, we will raise an error. There can be a few helper methods for the stack for convenience. For example, we can read out the length of the stack. So how many elements do we have on the stack? We could also check if a stack is empty, so we return true if the stack does not contain any elements, otherwise false. And we can also peek the top element. That's something else. So we can read the top element on the stack, but we don't remove it, because popping means removing and returning it, and top means just looking and reading the topmost element without removing it. But if you try to read from an empty stack, you would also cause an exception. And in order to make this more clear, we have some examples here. We are starting with an empty stack and we push a 5 on the stack. So push 5 means I have a 5 in my stack. If I push another 3, so the convention is now the stack keeps growing to the right. I push another 3, then I have the 3 at the top of my stack and the 5 at the bottom. I can also read the length of the stack, which is 2. I can pop. Popping means removing the topmost element and returning it. So the 3 will be removed and returned. We can check if the stack is empty, which is not the case because we have a 5 in it. If we pop the 5, we are returning it and the stack is empty. And if I try to pop from this again, I will get an exception. I can push another 7. I can push a 9. I can read with top the 9 that is at the top. I can push a 4. So now I have the 4 at the top, 9 in the middle, and 7 at the bottom, and so forth. So this is a series of stack operations that we apply to an initially empty stack of integers. And we will try to implement this now on our own. With this, I will screen share my environment again. What we need is initially a helper class that we call empty. And empty is just an exception class, or very empty inherits from exception, and it doesn't do anything on top. So if I have an empty class, or say an empty function in Python, I can just write pass, and it means like I just have an empty body, there's nothing in it. And empty is just a variation of exception. And so we don't need to raise an object of exception, but rather of empty, which is more specific. And we could add specific functionality later. So let's implement my stack. I need to initialize the stack. And what I could use now, if I wish, I could use the my array I have implemented before, but we will just use the native Python list because this one anyway works, and we have seen once how to implement the my array, and you have some more coursework to work with my array, but we will not use it. We've seen how to build it. We just use the Python list and we encapsulate it. We also want to know the length of the stack, and for this, I can just return the length of my data. So data is internally just a list, but since it's encapsulated, you could also just later change this to my array, and it will not affect the publicly visible interface. You just need to internally make sure that you're switching internally in all areas or all parts where you're using data. But data is just an empty list now. We want to know, because this was another helper method, if our stack is empty. And for this, we could just read out the length of our data and check if it's 0. We can also push. We want to push an element. And for this, we can just say we are appending to the data element E. Internally, we use this internally we use this list, and this list may need to resize from time to time, but this is something that is encapsulated. We don't care how the resizing works internally. We just use our list. We could use my array, and we've also implemented append on it, and internally it can resize. So this is all encapsulated. We can also implement top. Top means we can read the topmost element. And since we're using a native Python list, we can just use index -1, which gives us the rightmost element. It's the topmost element. Does this always work, or could something go wrong here? Maybe if you think it all looks fine, send me a positive reaction. If you think something could go wrong, send me a negative reaction. But so you think it could go wrong, all okay, but well, what if my stack is empty? Then -1 will not work. This would raise an exception internally from the Python list, but we actually want to raise our own exception. So we would check, is this empty? And if it's empty, we could raise an empty exception and say stack is empty. Because we are unable to look at the top element of an empty stack. And the last method we can implement is pop. And for pop, we also, first of all, need to check if it's empty. And if so, we raise an empty exception and say stack is empty. And now we need to do something on data. And it turns out, because this is a Python list, the Python list already offers the method pop. And pop means just remove and return the rightmost element. So this is being removed in our list and being returned to us, and we are returning what that function returns. If we implemented this with our own myList class, we would still need to do something in order to implement pop or remove an element. This is one of the things in the coursework that I had shown you, that you could also think about a remove method to remove one element. So feel free to switch this myStack implementation to your Python myArray that we implemented before. you would just need to improve, or you would just somehow need to amend your my array that you can remove an element, and then you would need to amend this line in order to use your my array adequately. We can also briefly test it. So we create an instance of my stack, and the stack is initially empty. We can push a 10, we can push a 100, and we will see we will now have two elements in it. We can see the top element is a 100. We can pop it, and we see there is a typo. So there was some tiny typos I've noticed, and that's why we've tested it, and it doesn't work, and we'll just fix it. It's all fine in the slides because I didn't write empty, and need to fix the typos. And here it was correct. So just because it's an interactive session, I have amended my stack, and we need to recreate the object. So we can push the 10, we can push the 100, we can look at it. There's a 100 at the top. We can remove it, and we can see now there's a 10 on top. The length is 1, and we can look at the top again, and we can pop it. Now we have popped the 10. We see it's empty, and if I want to pop it again, this will erase our exception in which we said the stack is empty. So we fixed the typos, and it works now. If you run this in an IDE, you would have some helper tools that would tell you early that there are some typos in here. But as usual, it's all without typos in the slides. We can think a little bit about the complexities in our stack, and the complexities that are fairly easy is the length. Length is O of 1 because we're just reading out the length. The same for top, we're just accessing an index and we're reading out that element, or we may be raising an exception. Similarly, we check if something is empty and return that value, or return a true or false. So all of these complexities are clearly constant. But pushing an element would be O of n, because it would be O of n because internally that list may need to resize, but because of amortization, because the native Python list would also just double its capacity when needed, because that worst case becomes so unlikely in average, we also use an amortized complexity and say it's O of 1 and it's amortized. But if you don't put a star or any link that it's amortized and you just say O of 1, that would be wrong, because then it would be O of n. Why do you think popping uses an amortized complexity? Why don't we just say popping uses O of 1, but an amortized complexity? Do you think you have a suggestion? Maybe green reaction, negative reaction, if I shall wait for you. If green reaction means you would see why we use an amortized complexity, and red reaction would mean you don't see it. So popping, we'll go back to the code. Popping here means we just pop the topmost element and return it. And if we used the myArray implementation we have done before, and we would just allow to remove an element, but we wouldn't include any possible resizing, then it would be just O of 1 because I'm just removing one element and returning it. But the Python implementation of the list includes resizing if it gets too small. As I said before, one threshold could be maybe a fourth of the capacity or a tenth, whatever. So when you keep removing elements from your list, but at some point you reach a certain threshold for which the list capacity is just too big in relation to the number of entries you're storing, then we would resize and shrink the underlying array. And this may happen in the native implementation of list in Python. And that's why popping is not just O of 1, but it could resize and become smaller, which would then be O of n. So O of n would be the right complexity for popping, but for popping, it's even less likely to resize, and it's super rare that this would happen. So we also put the O of 1 amortized complexity. O of n would be wrong, or O of n would be correct, but maybe imprecise. O of 1 would be wrong. So we say O of 1 amortized. And feel free to implement a more advanced my array that you can plug in here in order to remove an element. Maybe you could call remove on the topmost index, and before read it out, you could implement pop also in your my array, which would just remove and return the rightmost element. You could also think about resizing when it gets too small. So all of this is available for you to test out in a few lines of code. It's not part of the coursework. The coursework addresses some other problems, but overall, it could give you some good practice. Now, stacks are something you're using all the time in your operating system. Whenever a function call is executed in the operating system, you're using a stack internally because you're just putting one more function context on top of the stack. And in that function context, when you run a new function, you would store for the old function, for example, the register values from the CPU and some other environment and context variables. And later, when your new function terminates, the old function would be executed again, and then you would take the values, say, for registers and so forth back. So your operating system heavily uses stacks internally in order to execute function calls. You can use stacks very neatly to actually reverse data. So to reverse the order of a list, because you could just put all the elements on a stack and then you would start popping. So you would get the elements just back in the pre-order that is just the inverse or the reverse order of before. If you say, if you match tags in a markup language like XML or HTML, or if you match delimiters, for example, you want to match these opening delimiters in the right order with the closing ones, you could also work with a stack. You would put this one first on the stack, then this one, and then this one. And when you see a closing delimiter like this one, you would check if the opposite one, so the this one here, would be at the top of the stack or not. If this one came first, and then say if these two were just reversed, if this one came first, it wouldn't match the opening delimiter on the stack, and then you would raise an exception. So you can use a stack quite easily in order to match delimiters. So if you parse for example, a programming language, or if you parse a markup language like XML or HTML, you can use a stack very easily for this. There's also some coursework on stacks. For example, problem 9.6, there's the so-called postfix notation in order to express mathematical operations in a different order. And if you want to evaluate them, this first of all looks very tricky, but take a look in the book. And with a stack, you can solve this in a few lines of code. So overall, that is something quite interesting. And stacks are super helpful. You'll need them for a lot of your programming problems in the future. So spend enough time on the coursework. So we will now look after lists and stacks, because stacks are just a variation of lists. We will look at another variation, which are so-called queues. And we will always look at the abstract data type and first see what the behavior of the data structure is, and then we see how we can implement it. And the queue has, again, two methods. We can enqueue elements to our queue. An element E would be enqueue to queue at the back of queue. So we can say, for example, the right end of the queue. And we can dequeue elements from the left. So we remove and return the first element from the queue. So at the left end. Remove and return, and if the queue is empty, we will raise an exception. So a queue, it's like you're queuing at the supermarket or at Disney World. You're queuing at the end of the queue, and the frontmost people, they pay their ticket or get their ticket checked, and they can enter. And slowly you're moving also to the front. Queues have numerous applications in computer science. We'll see them later. And we will first think about a few more methods for convenience. Convenient could also be to read out the length of the queue. We could check if the queue is empty. And queue.first would return a reference to the first, so the leftmost element. Without removing it, we just read it. And then error will occur if the queue is empty. And let's look at a sample example queue again. The queue is initially empty. We will enqueue a 5. So the 5 is put here in the queue. We will enqueue, and the leftmost element is the first element, and the rightmost element is the last element. Here, the 5 would be both the first as well as the last element. Now we're enqueuing a 3. So the first element is a 5, and then the 3 is the last element. The length of this is 2, and we can dequeue. That means we take the left element and remove it and return it, and we only have a 3 left in the queue. The queue is not empty. We can dequeue again and remove and return the 3. The queue is empty. If we try to dequeue again, we raise an exception. And then again, we can enqueue a 7, a 9, and a 4. And if we have this 7, 9, and 4, and we dequeue, we return the 7 and remove it. Does this behavior look okay to you? Maybe just thumbs up, thumbs down if you understand the behavior of the of our queue. Looks okay. Now we can try to implement this. And what we can do is, if we have a list, we can pop on the list, so the native Python list. And we can pop with an index k. And if you remember, we've just used this before, and we said here pop. But if we don't use an index, we remove the rightmost element. But you can put in an index. You can put, for example, index 5, and you remove and return in the element at index 5, if it exists. You can put in a 0 to remove and return the leftmost element. So there's a parameter, an optional parameter you can set. So we could think, if this is our list, enqueuing means appending, and dequeuing means popping at index 0, which would return and remove this element. So we could try to implement this fairly quickly in Python. The problem is it will be super inefficient because pop zero, yes, works. We can intentionally remove and return the first, so the leftmost element. But it will lead to problems because it's an array-based list, and removing the leftmost element means internally a new array needs to be created and all the elements are copied except the first one. So the element that was at index 1 would then be at index 0. I will visualize this for you on the iPad so it will make more sense. Just switching to the screen share. Screen share will be there soon. So pop in a list. So what I have are the elements here. So index 0, 1, 2, 3, 4, 5, 6. And if I pop here, so we call this L, we say L.pop, it just removes this element. And this can be done in O of 1. Concretely, O of 1 amortized because popping so now the screen share should be working. If it fails, please ping me in the chat because I don't see it immediately. So if I pop and I don't specify an index, it's just the rightmost element. And this will be done in O of 1, but ideally we also think about that popping, we've seen it before, could lead to a resize, to a shrinking of the internal array if we have, say, more space on the right that we have reserved for extra capacity that we are not using. So ideally, we don't say O of 1 because it could be O of n if it leads to a resizing, that it shrinks smaller. So we would say O of 1 amortized. But there is another situation that can happen. So we have our list again, and we have our elements. And what could happen is, say, I want to pop this element. Somehow, this needs to be done. And we cannot just remove this element. This doesn't work directly. So L.pop at index 0. But a consequence would be, because we cannot just leave an entry empty, that we need to move all the elements by 1. So one way to implement this is either to move all the elements or to create a new array and copy into it. But we cannot just leave index 0 empty because internally all we are using is an array. So what do you think the running time would be of this when I pop element 0? O of what? I'll wait for your suggestions in the chat. So O of what? It's O of n. One student suggested O of n squared, but it's not O of n squared, but it would be O of n because I need to move all of these elements. And we could also have some other situation, look, something like 0, 1, 2, 3, 4, 5, 6. And we imagine this is now much longer, say up to 100. And I would remove this element here, then it would be L dot pop at index 5, and I want to remove this, and then I still need to move all the other elements from the right, one forward to the left. So this would still be O of n. It's not fully n because there's still the k, but we assume now the k is relatively small. And when we looked at the list before, then we looked on page 154 on the mutating ones. The book actually suggested this would be O of n minus k, something like this. But overall, not too great. Um, so, and the problem is, this case here is not relevant to us. It was just an extension, but we are actually popping here the leftmost element, and then we really have to move all of the others here to the right, to the left, from right to left. So this is quite inefficient, and we will deque, because this is the deque operation. I'll write it out in a second. Deque, this. And deque is one of the fundamental operations in our queue because we either enqueue or dequeue. So this one here would appear very often. And in fact, this is not just O of n, it's actually theta of n, because when I pop the leftmost element, really all the other ones need to be moved to the left. So this is quite inefficient, and actually using our deque operation will happen often. So this is not the way we should implement it. We can implement it, it works, but in this course, we not only want to implement algorithms and data structures, but actually implement them efficiently. We need a different way to implement our queue. Concretely, we will implement so-called circular arrays, and the circular array works the following. In the circular array, we will have a reference that is called front. And front will be the beginning of this circular array. We will see very soon why it's called circular array. And for now, we just imagine it's a list or an array, and we are doing something. We can add elements. Say we add an element 1, or say a 10. What would happen then is the front would refer to the next one. Well, I'll just check briefly how I have implemented this because I want to use the same notation as I have implemented it for later. So just wait a second. Now, we'll keep the front here because I want to use the same notation as I've used in the code. But we will also have a size. And the size is our other parameter or other attribute. And the size was initially 0. And when we have added a 1, or the first entry, then the size is, well, not 10, the size is 1, because we have added one element. So we will have a combination of front and size. When we add this together, it would have first referred to here, but then we added one element, and we increased size to 1, and now it points to here. So if we have a new element, we would put that element here, say a 5. And the consequence would be that the size would be 2, and front plus size would refer to the next index. So I'm removing this, and the sum of this would be referring to this index. And I'm just putting the indexes up here. So this is index 0, index 1, index 2, index 3, and so forth. So front plus size will always be the index to which I'm adding the next element. For example, if I add now value 6, I would put it there. The size would be 3. And front plus size would be moved to here, where I would add the next element. Maybe just confirm if this part of our circular array, which is not circular yet, but that approach makes sense to you. Green or red reaction, depending on if it makes sense. So only positive reactions. Now, I want to be able to remove an element. So, because we've always enqueued elements right now. So enqueuing means adding more elements to the right. And now I want to be able to dequeue elements. And I want to dequeue the 10. And I don't want to call pop 0, but I could just delete this value and switch the front by index to here. I also need to update the size, which is now 2, because I have elements 5 and 6 left. But the front now refers to index 1, and the size is 2. So 1 plus 2 is 3. So new elements would be added in here. And I can pop again, say or not popping, I'm dequeuing. So the front would link to here. I would have only one element now left, the 6. And if I add an element, I would add it at index 3. Now, if I keep adding, we'll keep adding here, there. So it will keep adding and adding. And at some point, I'm here, and I have added an element here, and I want to add more elements. I don't have space at this end, but I have space at the front, which is here. And that's why I need a circular array. So once I'm here and I have added an element there, I would go with that circle from the end of the array to the beginning. And if I have space at the beginning, because I have moved the front further by dequeuing, I can keep adding elements here and there. And only when this is full as well, then I'm unable to keep adding more and I need to resize, because then I'm full. I need to resize at some point, but only at the very end, when I have also filled these elements. And the front will be moved further to the right when I delete elements. And front plus size is that index to which I'm adding next. Maybe just confirm if this makes sense to you, how I have visualized it. Green or red. And the beauty of this is it's highly efficient, because the only very complex operation in terms of the high complexity is resizing, but I have this anyway. But enqueuing is simple, and dequeuing, because enqueuing just means adding an element. Obviously, with enqueuing, I may need to resize, but I have to do this anyway, also if I use my regular list as before. But dequeuing is very cheap, because all I'm doing is I'm returning an element and I'm moving the front to the next one. And this is exactly what we want to implement now. And it turns out this is actually fairly easy to implement. And we'll implement this now together, step by step. So we will implement myQ. And we introduce a default capacity, and say it's 10. We want to initialize it. I want to say, well, we need initially a list with none entries, and we want my queue dot default capacity many. So default capacity could be 10 or whatever, but I take one list with a none entry and I multiply this with this factor like 10. And what this gives me is a list with 10 none in entries. So that's the capacity of what I can store in here. I also need my size, and size is 0. And I need my front index, and the front index is 0, which refers to 0 where I'm starting to add, or I'm adding at front plus size, but front is the one where I'm later dequeuing from. That's what I have visualized. I need my few helpers. I need to be able to find the length. I'm just returning self.size, and I want to know if it's empty, and I'm returning if the size is 0. Now, these are all the simple ones. The more complex ones will come now. Let's start with first. First is a helper to read out the leftmost element. And what I want to return is self.data at index front, because front refers to the leftmost element, initially 0, later the front may be increased once I start dequeuing, but I look at my data, which is my list at index front. What could go wrong here? Do you see what I may have missed in this implementation? If you feel you see it, send it to the chat. One person wrote it already. If the list is empty, yes. Is empty. Then we raise our empty exception and we write queue is empty. I started a new Python session, or IPython session. So later I also need to recreate my empty class, which we just maybe one of you can remind me that we need to do this once we have implemented the queue, because otherwise we create an instance of queue, but empty is missing, and I may forget this at the end because I'm now implementing all the other stuff. So maybe one of you, in case I forget to recreate the empty class, you just ping me later once we have finished the implementation of the queue. If you don't remember me and I forget it, we'll get the exception. Let's see. Then we need to be able to implement dequeue. And dequeuing means we are we need an answer, what we return, and this is data at position front. And we need to return that answer. Does that look fine to you, or is something missing? If you feel something is missing, send this to the chat, because there may be quite a few things still to do. I'll see what you think we may need to do together now. If you feel it looks okay overall, green sticker. If you think something is wrong, send a red one. So maybe some more reactions. So I shall explain the dequeue again. The dequeue means I'm returning the leftmost element, so the one where the front is referring to. So this is the dequeue. I'm returning that element where the front index points to. But we also need to be able to, first of all, we need to say, well, we have just removed an element, so we need to also reduce the size by 1. We also say, well, I have this answer, and my convention was that I'm storing always none entries for the unused spots. So I can say, well, where the front is pointing to, I put in a none entry. I also need to update the front. We've seen this before, that we increased the front. So the front is something we could say it's self. Well, we'll just keep it simple for now. We increase the front by 1, so we move it on the right and reduce the size and return this. We'll go back to the visualization in a moment, but we also need to check if we can actually dequeue something. So we need to check if it's empty, and if the queue is empty, we are unable to actually dequeue. And the answer was, I'm looking at where the front index refers to. This is my answer. I want to return it. But I also want to put at the front a none entry, because we started with none entries. The front will be increased by 1 to move it once to the right, and the size will be reduced by once and answered. But we'll go back to the visualization on the iPad, and we'll see if all of this is sufficient. Because this here is the front, and we said we've moved it to the right by once when we dequeue. And we updated the size. But now one thing could happen, and I'm putting this in green. The front may later, like dot, 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 as we evolve this, the front may be referring to this index at the very end. And I've noticed, well, this program got closed. Don't know why. We'll have it again. So we have this front index here, but now I'm dequeuing again. Where would I move the front index? Because we've increased front by once to move it here. Always step by step, move the front over, always +1. But now I'm here and I'm dequeuing again. What do I do with my front if I dequeue again? Where do I move it? If you feel you see it, maybe green reaction or red reaction if you don't see it. And if you see it, tell us in the chat where you think we should be moving the front now too. Maybe some more yeah, at index 0, that's correct. So the front would also need to move to index 0. So just increasing the front by 1 is not enough. We need to do a little bit more. And for this, we'll go back to our code. So the front +1 does not work. We need to actually say it's front +1, but I need to do something with it because it may be the maximum value, and then I want it to be 0. So I can use a modulo operation, and I can use the modulo, the length of the data. Length of data is just the length of the array. And when I have reached the maximum value and I'm adding, so by adding +1, so the maximum value would be the valid one, and I add 1 on top, then at some point I would be in an invalid index when I add +1. So I need to take the modulo. So say I have a length of 10, and the maximum index would be 9, because from 0 to 9. And I'm adding 1 on top, I would be at 10. 10 is an invalid index, but 10 modulo 10, because the length is 10, would be 0. So the front would be 0. Maybe just confirm with a reaction if this makes sense to you. Good. So the modulo is crucial. We will implement two more methods. NQ is also needed because we need to be able to add something. And we need to find the index where I'm able to add something. So we can say this is the available index. And we've said before, we've always added front and size together and said this is the available index where we are putting something. Because front is the very leftmost one, and we have size many elements. But this again, it's a circular array, may lead to an invalid index. So I also need to take this modulo, the length of self.data, because front may have moved within the circular array and I have more elements than I can fit on the right. And then I need to take the circle and go back and put in more elements there. And that's why self plus front is modulo the data. And then I'm storing the element in data there. So the element E, and I'm also increasing the size by 1. There's only one thing missing. My queue may be full, and I need to resize it. Because initially I can store 10 elements in it, but it could happen that the size is the maximum. And if size has reached the length of data, then I'm actually full. I'm unable to add more. And if I don't check this now, I will override valid elements that I'm not allowed to override. So I can say I will double the capacity again. So doubling the capacity would be 2 times the current length of our data. And doubling again, because we want to take advantage of amortization and that average as before for the lists when we looked at it. Now, the only thing that is left is resizing, and we need to resize our list. And what we need to do here is a few more details. I have a variable old, which refers to the current underlying data structure. And I will create a new data set that I will work with. So as before, we created a list with non-entries of a certain length. It was length 10. Here it's capacity, which is a larger one. You could obviously also amend your deque that if you keep removing elements and you have reserved too much space, you could also resize and reduce the size, something you could do. And then what I need to do is I need to copy all the elements from the old one to the new one. And for this, I create a helper variable that I call walk. And it's just where the front starts, so the leftmost element in the circular array. And then I go through all the indexes from 0 up to the size. And I say, in my new data, index k, so the new one, I'm starting with the 0. So index 0 will be the first element in my new larger data, but I cannot put k in the old one, but I need to put in this walk index because front may not be 0 with my current circular array. So I'm saying I start at front, which may be 0, could be 100, whatever. And then I'm copying from that first index in the old one to index 0, which is now the first index in my new data. And all I need to do is I need to update walk and go to the next index. But walk plus 1 is again not enough because I may have this circle And that's why I need to take it modulo the length of the old one, which was initially 10, but as it keeps growing, this value keeps changing too. And then at the very end, when everything is copied, I set the front to 0 because the first element in the new data is 0 because I started here with 0 and I've done the resizing. So one thing was missing. Do you remember what is missing, what you should remember me about? I'm remembering what I need to do. The empty class, as we've used it. And we can try to create our queue now and work with it. So the queue is my queue. And we can see the length is 0. We can enqueue a 5, say a 5, a 50. We see we have 2 elements. We can dequeue, we get the 5, we can dequeue again. Now the length is 0. We can enqueue a 500. We can also look into the front. It's considered to be private, but we can read it and we see it's 2 because we had dequeued twice. We could keep working with this now and test all the functionality that we had implemented, also that this circular walk works, but it's something you can test at home and put in some more data and try it and see if it works. I hope there's no typo in it. Well, we never know, but in the slides and in the resources file, you find the correct implementation. So I hope there's no typo in here, but looks okay overall. This is our queue, and what I have implemented is also available here in the slides, as you can see. And we've just done exactly the same. We did not put the empty class here again, so you would need to also type it as we have just done. We can look a little bit into our complexities, and we see obviously reading the first element, checking if it's empty, and the length is constant, O of 1. And enqueuing would be O of n with our traditional framework, because in the worst case, we may need to resize, but because in average, this becomes so unlikely, we introduced today the amortized complexity. So we say it's O of 1 amortized because we always keep doubling the capacity. If you just added 1 on top in the capacity, then this would be O of n either way. So the amortization only works, for example, if you double or probably triple, you would have a comparable outcome. Then it's O of 1 amortized. And the dequeuing is actually O of 1, the way we implemented it. But obviously, if we added one more thing that you could remove or that you dequeue elements, and if you reach a certain threshold, like a 4th or a 10th or whatever of the capacity, you would also resize. And that would be O of n, but we want amortized complexities. So it's O of 1 amortized. We did not implement that case that in your dequeuing you may need to resize, but you could add it if you wish. So these are the queues, and there are lots of applications for queues in computing. For example, in scheduling, when you schedule in your operating system more processes or threads, you're adding them to a queue, and then the scheduler always picks processes and threads from the queue and dequeues them, gives them a few time slices, and then puts them back to the queue as we would enqueue that one again. You can also have obviously multiple queues in a scheduler with different priorities. You could also think about I/O buffers or input-output buffers when you work with external devices. You enqueue the data coming in, you enqueue it in the buffer, and once your task takes data from the buffer, it dequeues the data. Uh, the literature also proposes so-called double-ended queues, which have a strange name, which is just DEQ, a double-ended queue. And a double-ended queue is an instance D that allows us to add elements both at the left and the right. So we would add elements to the left, add elements to the right, and we could delete elements from the left, which would be our dequeue, and our enqueue would be adding the last, but we can also now add on the left and remove on the right. We are not implementing this here, but it's been proposed in the literature, and you would have some helper methods like first and last and is empty and get the length. But personally, I think there's a very, very limited amount of applications for this. I just wanted to briefly mention to you what a double-ended queue would be in case you ever come across this term. We're not implementing it here because it's overall something quite rare, but feel free to implement it on your own if you wish. And with our circular approach, you could just amend it that you have a circle in both directions, and you could also walk to the left and not just to the right. So using this approach we've introduced, it wouldn't be that difficult to amend the circular array to implement a double-ended queue. Actually, maybe that's something I could put in the exam sometimes. I'm not saying I'm putting it in the exam this year. Obviously, it could happen as every topic in the exam, but I just have some notes here of questions that we're putting in the exam maybe in the next few years. Maybe one thing for the exam could be how to amend this to work in a double-ended queue. But it's not a hint for this year's exam, but also not an exclusion. It just came to my mind that using the code we have already, it would be fairly easy to adopt and implement a double-ended queue. There's also an example here. Adding the last element is a 5. Adding a first is a 3. Adding a 7 on the first would be then 7, 3, 5, and you can delete last and first. But I think the number of applications for such double-ended queues is quite rare. For queues, there is a little bit of exercises in the coursework. So the coursework sheet for lists is quite big, and it's something for which you have plenty of time, both next week, but also today after the lecture. I'll briefly stay in Zoom in case you have any questions about the lab, and I'll be happy to help, which won't be recorded. And then we have on-site lab sessions next week again to study the coursework together here for lists. But there'll be more than enough coursework for you now after this lecture. We have done most of the lists, but all the lists we have implemented today are based on arrays. We've built the myArray class that is built on lists. We have used a lot the Python list, which is based on arrays internally. But there is a second approach to building lists, and these are so-called linked lists, which is a totally different approach, and it's an alternative to an array-based sequence that we have always relied on. Both of these approaches so both the linked list as well as the array-based list we have always used, they keep elements in order, but they use a different approach. And the linked list is something I want to introduce now today for the end, and we will see what a linked list is. In fact, we are creating objects of so-called nodes, and we connect these objects together. And each node contains a reference to its element as well as the neighboring nodes, maybe the next one or the previous one, depending on how you build it. We will discuss the linked lists now, and we will implement a linked list, and then we will compare it to the array-based sequence and see some pros as well as some cons. We will first study a singly linked list. And the singly linked list is fairly easy. It looks something like this. We are not working with arrays now, but our list has a head and a tail. The head is the first element and the tail is the last element. And each element is in fact in a list such a node, which is not these nodes, they are not stored next to each other in an array, but each node is stored somewhere in the memory. And the head refers to the first entry. The first entry refers with a memory address to the second entry. The second entry refers to the third entry. The third one to the last one. Tail also refers to the last one. And the last element has no successor, so its next reference is just a non-reference, just an empty reference. And then the node contains also a reference to the value. So the value is an object, could be a string or some other object, but that's as before, where we stored in our array memory addresses to the actual objects. That's what we have always done. But now we don't have an array, but we have individual nodes which are spread throughout the memory and that just refer to each other. So what is this structure helpful for? It has various pros and cons. One advantage is I don't need to reserve an array up front because sooner or later I may need to resize the array. I don't need to resize when I have such a node structure because just the nodes refer to each other. It's a huge advantage. There are some disadvantages. Maybe I need more memory because these objects also need to be stored somehow. Creating a lot of objects may take a little bit more time. And I have one big problem. I'm unable to just randomly index some element. I was able to do this with an array because the array was a fixed size entry in the memory. And I could just index k, which could be 0, 5, or 10 in constant time. I'm not able to do this anymore because these pieces are spread out through the memory. So I cannot just access them in constant time. In fact, I may need to maybe start from the head, walk to the first element, then to the next element, and so forth. So I would need to walk to element k rather than accessing it directly as if it was an array. But we will later contrast again the differences. But one advantage is I don't need to reserve an array up front and I don't need to resize this anymore. And there are some other interesting things I can do. For example, I can also create an element at the front very easily because this is my linked list and it's a singly linked list. Singly means always one node refers to the next node, always one link to the next one. That's singly linked. And I can even create a new first element, a new head element. I would just create a new object, and that new object would refer with its successor reference to our current head element. And once we have referred to this, we would switch the head to the newest element. So adding elements to the front or even in between is easy because I don't need to just, resize an array or move stuff around, but rather I can just switch these references. So this is fairly interesting with a linked list. And obviously, I can also add new elements at the tail very easily because I just go to the tail, which refers with its successor reference to an empty memory address or a none address. I create my new object, and then all I'm doing is the tail object will be referring with its successor reference to this new element, and I'm also switching the tail reference to my new object. So I can fairly easily create new objects, add them at the beginning and the end, and I don't need to resize or create a new array. I can also remove elements. I can remove the head element very easily because I can just switch the head reference to the next element, and then I'm deleting the initial head element. But in Python, I have garbage collection, so this is deleted automatically for me because no one is referring to it anymore, because the only one that was referring to that element was the head, and the head is now referring to the second element. So I can fairly easily also remove elements. So before, when we implemented our queue, we could have implemented the queue as well as a linked list, because we used for our queue the circular array approach, but we could also use a linked list approach to build a queue. And this is actually one of the coursework problems, 9.7. You're tasked with implementing a queue using a single linked list. And then you don't need to walk around anymore and work with this as we've done, because you can just add elements to the right and remove elements from the left. And you don't need the circular array approach anymore. So that's why this is one of the coursework problems this time. And I'll show you now how we can implement something like this on our own. What we need is object orientation. So we need to be able to create new nodes. And when we had the intro to Python, like 4 or 5 weeks ago, I've also showed you how to create your own classes, how to create objects. We've done this today already, and we'll do exactly the same for a linked list. But we are not building a linked list, we are building a linked stack. So a linked list we've seen now in the slides, and we're just using this to build a stack with node elements. So what I need is, again, an initializer, and I will have the head reference, which refers to none, and a size, which is 0. And I want to know the length of this structure. And I'm returning the size. And I want to know, is this structure empty? And I would just return if the size is 0. Now it will become a little bit more complex, because we have just built the simplest methods to initialize our stack and to read out the length and if it's empty. But we need something else. We need our nodes. And for the nodes, we will create a new class that is called node. In Python, you can have a class within a class. Have you ever seen this in other programming languages? Quite some other programming languages offer this, a class within a class. So an inner class. Only seen negative reactions. Also works in Java, by the way, that you can have inner classes. And we need a node class. And because these nodes are only relevant to the linked stack and not to other classes, we just say it's an inner class that we consider private, and we don't want it to be a different class outside linked stack, because all we need is that we use it right now in here. So that's why we use an inner class. And for the inner class, we also have an initializer. We want to initialize our node, because we'll create plenty of node objects now. We want to have a value, so the element value in our node. And we will also have a next reference to refer to the next element. And well, we don't call it just next, because you're wondering why is next green, because next is a keyword or a reserved word in Python. We'll need this for iterator, something we see in a few weeks. So maybe we just call it next element, and then it's not green, and we don't block the or we don't use the reserved word next for iterators. But iterators is something you'll see in a few weeks. So, and then in our node, we are storing what we have received as an element value. So it's we create the attribute element and store element in here. And we also store the next reference in underscore next. Underscore next is a fine term which doesn't appear green, but next did. That's why we called it next element. And then here next element and store this in underscore next. And it's very important that you indent all of this correctly because we have our class linked stack and we have an inner class. So all of this is indented by 4 spaces. But then we also have, again, the actual methods of our linked stack, and this is the inner class. So make sure this is indented correctly, that this is your inner class, and this is the methods that we actually need. And one question was, what is the self.head? Head will be the first element in our stack. We'll later see what first actually means. But when we looked at before in the slides at the visualization of a linked list, we said we're not storing an array, but somehow we need to refer to the first element, to the first node that is somewhere in the memory. And that node I refer to with head. And then that node refers to its next element, the next element to the next one, because we don't have an array where all of this is stored. So we somehow need to make sure the order works this way. And now we can push a next element. So pushing on a stack means I'm putting an element on top of the stack. And this is now not a linked list, but a linked stack. So the head will initially, when I have an empty stack and I'm pushing, I'll say I assign something to the head and I'm creating a new object of this inner class node. And what I'm doing is I'm passing a value e. So I'm creating a new node with value e, which can be an integer or some other object. But then the node has a next element. And my convention in this linked stack will be that head always refers to the topmost element in the stack, because the topmost one is the one I want to remove or read from or put something again on top of it. And that's why this next element reference in a node will refer to where self.head has been referring to up to now. And initially, self.head was none. Now, self.head is a new node, but that node refers to where self.head referred to before, which is none. And if I stack one more element on top, so the second node, I'm creating a new node, and that node will refer to where self.head referred up to there, which was the old head, and now head refers to the topmost element, and the topmost element refers with its reference to the one before. There's a question why we didn't create a tail. The tail is optional, and the tail was maybe interesting for a list where I wanted to refer with the head to the leftmost element and with the tail to the rightmost element. But now with a stack, I actually only care about the topmost element. And here head means the topmost element and refers to the element that was before the topmost element. And what I also need to do is I need to increase the size, because I don't have an array anymore from which I can read the length, but rather I store a certain number of nodes. And in order to read out the size efficiently, I store this as an attribute and I increase it. I don't need to store the size. I could also leave this out, but then I need to recompute it when I call length. And recomputing would mean I need to count all the nodes, which would be O of n, but I want to read out the size in O of 1. That's why I need one more variable to count. I can also check what's the topmost element and just reading the topmost element. So I can check self.head.element because self.head is the actual node, but with top, I want to get the value that is stored in that node, and that would be the dot underscore element, which is the actual element value. Something can go wrong again. I cannot do top if the stack is empty. So I need to raise my empty exception. Later, I need to create that class briefly again because I started a new IPython session and it's not empty is empty, but stack is empty. So stack is empty, and then I raise an exception. And if that's not the case, I will read out the value. And the last method is pop. And popping is just self.is empty as before. And I need to do a few things now. I need to store what's the result that I want to return. So I'm taking the head and its element value, and I store that element value in res. Then I want to return this at the end, but I need to do a little bit of tidying up because with popping, I'm not just reading the topmost element, but I'm actually also returning it or deleting it. So I need to say I don't need the topmost element anymore. And I just want to get rid of it, that topmost element, because later I will return that value, but I need to get rid of it. So I need to say the head will have a new reference, and that new reference is is the successor of the head or the next element. So the element just under the head, where the head always where the node refers to, because we've always said when we push, that node just refers to where the head referred to up to there, which was the topmost element. Then I'm putting a new element on top, and that one is referring just to the element under it. And now when I want to get rid of the head, because I'm popping, I say the head has now the reference to the element under the head, which was the next one. And I also need to update the size, because size is now -1. And I've created my linked stack. I also need to create this one here again. So are you okay with this implementation of our singly linked list building a stack? Maybe green or red reaction? Only see positive reactions. So seems to be okay. Let's test it. So we want to create a stack, and we've called this linked stack. The length is initially 0. We can push a 10. We can push a 100. We can push a 1000. The length is 3. We can top the element, get the 1000, and we probably have a typo somewhere because it doesn't work as we expected. But we'll figure this out. There's a typo because what we see is in top, we try to return self.head.element, and it says it has no attribute element, and something went wrong. If you see what went wrong, tell me, because I frankly don't know what went wrong in the So we made one minor mistake in the push. We needed to say it's head. So this it's obviously all correct in the slides, and So we need to recreate the stack. And then we try it again. So just for those following the recording before, we forgot the underscore here and putting the 1000 on top. This is a live demo, so sometimes the stuff doesn't work as expected. And we see now the top is the 1000. We can pop it, and the length is now 2. We can pop it again, is the 100. We can push a 5, which we can pop, and pop the original 10. And if we pop again, the stack is empty. So overall works okay. And now we've built our second stack today, not using an array based approach, but rather uh, using the linked list approach. And for us, we have a few more things to do, but we are almost done with the lists. This is the implementation we have just done. As I said, there is some coursework that you can implement a queue using a singly linked list. We have always talked about singly linked lists. There are lots of variations of lists. You can also, for some cases, have a circular linked list. So you would have your head element and your tail element, and the tail element would refer with its next to the head element. And such circularly linked lists is something you may see from time to time. They may be used for certain cases, like for scheduling. So you could sort of walk through and say, I'm scheduling this task, then this task, then this task, and then I go to that task again. So this would be one approach, what we can use this for. One person asked them about the implementation before. The question is, or what the student says is, we can always access elements into the inner class without redefining them into the main class. Yes, so you create an inner class, and the inner class is something you can use within the class. So like we have node as an inner class with its functionality, which is just the initialization for which we create the attributes, and we create an object of node, and then we have these node objects, and the node objects will be accessed like this, for example. So the inner class just helps us to say that we have some features that we only want to use in linked stack, and we don't want to create a separate class outside because they may be used by others that don't know what to do with it. So rather, we put it as an inner class. Obviously, it's all public. It's not private in Python, but for convention, we put the underscore there and say it's considered to be private. Don't use it for other users than what we use it for within linked stack. So just another form of encapsulation. Did this help to answer the question? And inner classes, something we'll see maybe a few more times in this course, but it's something that appears in lots of other programming languages too, not just here in Python. So these circular linked lists would be, for example, used for scheduling. So scheduling can be done with a queue, what we have seen, but you could also have a linked circular list, and you can just walk to the last element. You could schedule that task and then go to the next one and schedule this again. So these circular linked lists have numerous applications, for example, scheduling as well as others. And as there are singly linked lists, singly linked means a node refers to the next node, that node refers to the following node, and so forth. You can also have doubly linked lists, and doubly linked lists mean that you have a node that refers with next to its next node, but that node also has a next node, next reference to the next node, but each node also has a previous reference to refer to the previous one. So this one here would have a next to SFO, but previous to JFK again. The advantage of a doubly linked list is you can walk through the list in both directions, forward and backward, which you cannot do with a singly linked list. With a singly linked list, you can only walk in that one direction. And if you wanted to take the opposite direction, you would need to start from scratch, from the head, and walk all the way through. So with the doubly linked list, you can walk in both directions, but you need a little bit more memory. Concerning memory, I just remember something. If you look at the slides, there was one more line that I did not implement for you in the note class. It's this underscore, underscore slots, underscore, underscore something. This is just a minor Python detail which helps us to use our memory more efficiently in the RAM by adding this, but it's not relevant for the remainder of the course. This is not a Python course to use the latest tweaks in Python, but rather this line here just helps us to streamline memory usage, but it's not really relevant for this course, just in case you see it. So with doubly linked lists, we can walk in both directions, but we need a little bit more memory because each node now has two references to other nodes plus the reference to the actual element, and you can manipulate doubly linked lists as well. There are some visualizations here, how you can insert a new element. Say you want to insert a new element between JFK and SFO. You can walk to JFK and create the new node and then update the next reference to refer from JFK to PVD, and PVD would refer with its previous reference to JFK, and you also need to link to SFO, and SFO needs to link back to PVD. So it's just a little bit more work working with these two references, and you need to do all the updates in the right order, but it isn't that difficult. And also, if you remove an element, like it's just the same kind of stuff you would need to do just in the right order. When you remove something in Python, we have a garbage collection. So if no one refers to this node anymore, it will be cleaned by the garbage collection. Same in Java. If you use Python and Java, you're done. If you use C++ or some other language which does not have garbage collection, then you would need to manually clean this in the memory, but nothing to worry about in Python. When I studied algorithms and data structures in my undergraduate studies, we used C++ in that course, which helped me to get a little bit of a better understanding of how all of this works at low level. But the lecture was not just 90 minutes per week, but 180 minutes per week. So we had more time for this. And while working with a more low-level language can help to understand some of these operations a little bit better, you need more time, but you also need far more code. And that's one of the reasons why I picked Python for algorithms and data structures, because we can describe most of these algorithms and data structures just in a few slides. And if we did this in a more low-level approach like C++, we would also need far more code, which wouldn't fit that neatly in a few slides. So that's, again, one of the reasons why I picked Python. And since most of you study AI, you will anyway be more exposed to Python than to C++. Now, for the end today, we can compare a little bit, again, our linked-based approach with the array-based approach. What are the pros and cons of both approaches? The array-based sequences, so all the stuff we did earlier today, that we use some underlying array, And the native Python list class also uses an array-based structure under the hood, has the big advantage that we can access elements in O of 1 much time, because we just can use a random index get in constant time that element, read it and manipulate it. The operations overall, or if you compare array-based sequences with linked-based approaches, you would see that things like you would typically see the array-based structure runs a little bit faster than the link-based structure. If the operations have the same complexity, obviously depends on the operation. But if you have two operations, one operation in an array-based structure and the same operation in a linked-based structure, and they have the same complexity, typically you would notice that the array-based one runs a little bit faster in terms of a constant factor. And also the array-based representations typically use proportionally less memory than the linked structures, because what you need for your array-based structure is the array where you store the memory addresses to the object, to the values. If you use a linked-based structure, you need to create the object. So each node is an object and refers to the values. Plus you have these next references and maybe even the previous references. So they need more memory, constantly more, but more. And if you have not just one element, but a billion elements, and if you need, I don't know, 1 billion bytes or 8 billion bytes, for example, it does make a difference. It's just constant differences, but constants eventually may still matter. So these are some of the advantages of array-based sequences, but they also have disadvantages, like resizing. Resizing is expensive, or deleting an element at the beginning or something at the left end. We may need to resize and move everything. We've seen some workarounds with the circular array, but that doesn't work for all the problems. It maybe works for a queue, but if you have a regular list and you just want to remove element 3, then you need to copy all the remaining elements from the right by one step to the left. With a linked-based structure, you can simply go to that element and remove it and fix the references, and it goes much faster. And this is one big advantage of the link-based structures. They support O of 1 time insertions and deletions at arbitrary positions. You still need to go to these positions because you cannot just jump to position 100. You need to walk there. So there's no random index to get there. But once you're there, you can do all of these operations in O of 1. And maybe, as I said, if it's like a constant number, like the third element that you want to remove, or the first element that you want to insert something, you can easily walk there, and then you can do these O of 1 time insertions and deletions. This is overall something very helpful that you cannot do with the array-based structures. And the link-based structures don't need to resize, and the link-based structures, they provide worst-case time bounds for the operations. With the link-based structures, we don't deal with amortizations, or the amortization we saw. They give us average bounds, but this is only relevant to the array-based ones and some other data structures we will see in a few weeks. But these link-based sequences, there we don't need amortization. In practice, in the real world, the array-based sequences are used far more often than the link-based ones because they need less memory, constant less memory, and you have this huge advantage that you're able to access a random index in constant time. Yes, you need to resize, but you can keep this under control. It doesn't happen that often because we double the capacity in each round. And do not underestimate the impact of caching when it comes to quick access, quick operations. Caching is nothing we've discussed here because it's done by the operating system for you, but caching has huge impact as well. and caching works much better with this array-based structure than with this link-based structure. So in practice, the array-based structure is used far more often than the link-based structure, but this doesn't mean the link-based structure is irrelevant. It depends on your problem. And if you have a problem for which the link-based structure may work well, please do so. So this is what we have done today. We've looked at regular arrays, then dynamic arrays, so resizing them. We call this lists. We looked at operations because the worst case is rare, but may be happening because of resizing. We looked at amortization, and then we built stacks and queues, both from array-based structures, and then we looked at link-based structures and built a linked list, and we've compared all of this together now. And we've seen the advantages of array-based structures and link-based structures. Next week, we will have coursework as usual. We will have lab sessions next week, plenty of lab problems for you to work on lists. Do work on this because the lists are a very important data structure we'll be using all the time now. And lists will also be the basis of maps and hash tables, for example. We need lists when we sort data, when we search data. So next week, after the coursework and the lab sessions, we will also continue with the lecture and we will do some work on recursion. So recursion means a function calls itself. And with recursion, we can address some computational problems very efficiently. And this will be the next two lectures. So next week and in 2 weeks, we'll be studying recursion. And recursion can also help us to design algorithms efficiently. And we will, for example, then look at sorting, for which we need recursion, because with recursion, we can take a big problem and break it efficiently into smaller problems and solve these smaller problems. This is an approach called divide and conquer. And that's what we will study in the recursion chapter. And I'm still now here for questions on the coursework in case you have them, but I'll stop the recording and I thank you for joining today on this special holiday. Quite some have joined and the others are watching the recording. And next week, if you have any questions on the content from today, I'll be happy to discuss this with you in the lab session. So take care and goodbye.